kiddos today, so huge change of plans. But we are going to finish the little portion that we have left of 6-3 notes. So I don't have them filled in on here because I'm using my computer at home and it's really hard for me to write. So be patient with me. So 6-3, the only thing we haven't done on these tables here is done the variance and the standard deviation. And so we've got to do that, and then we've got to compare. So if you remember from before, we were taking samples. So like they were giving us a population of just 4, 5, and 9-year-old kids, and then we were like sampling just 2 at a time. And so I know that I did not put this in the same order as what your table is, so pay attention to that. I went 4, 4, 5, 5, 9, 9, 4, 5, 4, 9, 5, 9. So as we're going through here, my variance and standard deviation might be mixed up from yours just because we put them in a different order. So be careful of that and put them in the right spots according to where they're at on your table. Okay, so we've got to calculate variance, standard deviation. And so let's do that real quick. But going through here, A, B, C, D, E, let's talk about what we've done and what we haven't done yet. So identify the list of possible samples and write them in the table below. We've actually done part A. That was the listing out these guys, 4, 4, 5, 5, 9, 9, that stuff. Find the mean, median, range, variance, standard deviation. We've done most of that. We have to do variance and standard deviation yet. And then it says find the average, mean, median, range, variance, standard deviation. We've done those for these 3. And then we have to compare that to what the population is. So these numbers right here went here for my sample, and now I'm comparing them to what the mean is for the whole population. So if I take the mean of all 3 numbers, or if I take the median of all 3 numbers, or the range of all 3 numbers, how does that compare to just taking samples of 2 at a time? Okay, so we said that yes, the mean was good because those were both exactly the same. The median wasn't as great, and then the range was not really very far on at all. So we just have to calculate variance, standard deviation, and answer some questions, and then we'll be done. So this is the formula from up above here. It's this guy. I've just copied him down below. Variance is that one. And then to do standard deviation, we're just going to take the square root of that number. So be patient with me as I write. This is not real great to write with, but here's how variance is going to look for the first one. So 4 and 4, we're just doing those 2 numbers. So when it says we need the sum, that means we're doing both of the numbers and then we're adding them together. So the first one, we're going to have 4, which is my x. My x's are the 4s, and then mu is the mean, okay? And the mean is this guy. So this is going to look kind of weird. For the first number, we have 4 minus 4, and we're going to square that. And we're going to divide by capital N, which is the number of numbers in my population. So the entire population has 3 in it, okay? Then I'm going to add to that. My next number is also 4, and the mu is still 4, so I have 4 minus 4. And some of you guys are like, why are you writing this in here? Because it's all going to go away anyway. You are right. I'm just showing all my work so that you can see how this works out. Divided by 3. So 4 minus 4 ends up being 0. Squared is 0. 0 divided by 3 is 0. This is still 0, okay? And 0 divided by 3 plus 0 divided by 3 is just going to be 0, which means my variance is 0, which should make sense because variance is how your data is varying. If I have 2 numbers that are the same, they're not varying at all. There's no variation there. They're identical numbers, right? If I take the square root of 0 for my standard deviation, that gives me 0 standard deviation as well. Okay, now you can just about imagine that 5 and 5 and 9 and 9 are going to have 0 for variance and 0 for standard deviation as well. And that is true because your formula will end up looking like 5 minus the mean for that, which is 5 divided by 3, and 5 minus 5 divided by 3. Okay, so let's do this one. Let's do 4, 5, because this one's going to look a little bit different if I do that. Okay, I'm going to do that in a different color. Let's go right down here. So 4 is my first number, and I'm subtracting the mean, which is 4.5. So here's what that one looks like. 4 minus 4.5. Whoop. 4.5 squared. And I'm dividing that by 3. Okay, then I add that to my second number, which is 5 minus 5.5. Okay, and that is squared, and we're dividing by 3. Okay, so let me get my calculator out. 4 minus 4.5 is a negative 0.5, and 0.5 squared is 0.25, and that's positive. So this is 0.25 right here, divided by 3. I should have done that. 0.25 divided by 3 is 0.083, repeating. So let's go 0.083. Okay, 5 minus 5.5 is going to be a a 0.5 is, why did I go 5.5? That shouldn't be 5.5. This should be 4.5 right here. Bleh. Somebody's yelling at the computer like, you did that wrong, Mrs. Comature. Yeah, I did. 5 minus 4.5. The mean is 4.5 for both of them. So mean here, this is my x number here. All right, now that I've thoroughly confused you, sorry. 5 minus 4.5 is a positive 0.5. Squared is 0.25. 0.25 divided by 3 is that 0.083 again. Okay. And now remember that they're both positive 0.083, because even though this was negative 0.5, when you squared it, it became positive 0.25. So both of those are 0.083. And if I add them together, I get a variance of 0.1. We'll go 167. We'll go 2 decimal places. Okay. All right. Standard deviation is the square root of that. And 0.408. Okay, that's my standard deviation. All right. Okay, let's do the next one. All right, same thing again here, but my numbers are 4 and 9, and I'm going to compare that to 6.5, which is my mean. So first number is 4 minus 6.5, and I'm squaring that, and I'm still dividing by 3 because there's still 3 numbers in my population. Adding that to 9 minus 6.5 squared, and I'm dividing that by 3. Okay, all right, so I got to do some math here. 4 minus 6.5 is negative 2.5, which is 6.25. I'm doing too much in my head. Let me try. Okay, I'm going to square it. 6.25 divided by 3. So this whole thing, I get 2.083. Okay, 9 minus 6.5 is going to be also 2.5, but it's positive 2.5 squared, which doesn't matter. It's still going to be 6.25. Okay, and 6.25 divided by 3 is going to be the same thing again. Okay, it's 2.083. Okay, and so my whole variance, if I add those together, is 4.167. We'll go. Okay, if I take the square root of that, I get 2.041. 2.041. Okay, all right, last one, I have 5 and 9, and I'm comparing that to 7. So I would take 5 minus 7, and I'm squaring, dividing by 3, and I have 9 minus 7 squared divided by 3. Okay, 5 minus 7 is a negative 2, but negative 2 squared is positive 4, and 4 divided by 3 is 1.3, repeating. So we'll go 1.33. Okay, 9 minus 7 is positive 2. 2 squared is 4. 4 divided by 3 is also 1.33. Okay, and if I add this together, I get 2.66. Should I go 2.66 or 2.67? I'm going to go 2.67 because that's what it would be if we rounded. Okay, and then I got to take the square root. 2.67. And square root. 1.63 is my standard deviation. Okay. All right, now when we go to do our totals or our averages, I'm adding all 6 of these numbers together and dividing by 6. Okay, so, I mean, really, you don't have to add the zeros in, but whatever. 0.167 plus 4.167 plus 2.67 divided by 6. So standard deviation, or variance, excuse me, I get 1.167. Okay, I'm going to put that in my totals down here for sample for 1.167. Okay, all right, here if I add my standard deviations together, 0.408 plus 2.041 plus 1.63 divided by 6, I get 0.680 if you round. Okay, 0.680. Okay, now we've got to do the variance standard deviation for my whole population, and then we're going to compare.
Hi, did you take a snooze? Yeah, hello.
Okay, I have a helper now, so. Yeah. You can sit right there. There you go. Okay. All right, so now we got to do the variance formula, but we're doing it for the numbers 4, 5, 9, and the mean again was 6. So when we're doing this formula, we've got to do 3 pieces instead of just 2. So I'm going to do 4 minus 6 squared divided by 3 plus I'm going to do 5 minus 6 squared divided by 3 plus 9 minus 6 squared divided by 3. Okay, all right, now 4 minus 6 is negative 2, squared is 4, so 4 divided by 3 is 1.33. Okay, 5 minus 6 is negative 1, negative 1 squared is 1, 1 divided by 3 is a 0.33, and then 9 minus 6 is 3, 3 squared is 9, 9 divided by 3 is 3. So if I add all 3 of those together, my variance I get is like 4.6, and I'm going to go 6.7 just because that's what it would be when I was rounded. So now we're comparing this variance versus this one. Not really. Not really very close for a variance at all. Okay, standard deviation, if I take the square root, it's going to be a little bit closer, but I'm still going to say for this is not going to be great. We take the square root, 2.16 is what we get for standard deviation. So again, we're just square rooting 1, 6, not 7, 1, 6. So, I mean, it's a little bit closer, these two numbers are, but I'm going to say better, but it's still not good. It's a better indicator. Standard deviation is a better indicator, your sample versus your population, but it's still not great. Variance was really, really off. Now, again, this is just what we get for our data. All right, we're comparing our sample mean variance standard deviation that we got from this table to the population of just those 3 numbers. All right, now if we go down to on the second page of the notes, this is what in general, now for these were the results that we just got for this table. In general, what should happen is that proportions, which we didn't do any proportions today, but any proportions, any means, any variances usually are good estimators. That was not the case in our example. Our variance was not great. Okay, our mean was good, but variance was not good. Okay, biased estimators, which are not good estimators, not good typically. Okay, in general. Now this is like encompassing all samples of all populations and stuff, if we would do this over and over and over again, typically we would come to this conclusion that these would be good and these would not be good. So median would not be a good one, range would not be a good one, standard deviation would not be a good one in general. According to ours, you can go ahead and leave these in here, good estimator, because according to our data, these were pretty decent. But in general, the ones that we are allowed to rely on are these guys. So if we are going to use a sample to represent a population, we can talk about these things and take the shortcut of using the sample when we're dealing with mean and variance, because those do usually provide good indicators. Again, for our sample, it did not. We were also only using 3 numbers for our population. So if we would take a larger population and deal with those numbers, it would probably be different and result more in this split. So typically the median is not a good indicator, not a good reliable number. Your range is not very reliable and your standard deviation is not very reliable. Okay, so I'm going to read the important note. The sample standard deviations do not target the population standard deviation, but the bias is relatively small in large samples. So if we would have a larger sample, we only had 3 numbers in our population, but if we would have a large population and a large number of samples, we usually use standard deviation because it's the amount that it's off by is relatively small. So yeah, it's not as good as what variance would be in larger populations, but we usually are allowed to, talk about the standard deviation at least, even though it is a biased estimator. Well, yes. You got tired of reading your book? Okay. So, that was clear as mud. Section 6.3 is not my favorite section, so sorry about that, but it's something that we have to talk about. That's what statisticians do. We look at samples versus populations because we want to be able to go the sample route. We do not want to sample entire populations. When there are only 3 numbers, that's not bad. But when you have huge populations, we would rather take samples and samples and samples of those, average them together, and use those results rather than using an entire population. So we're trying to use, in section 6.3, we're trying to compare the two to say, like, do they even give us good results if we were to try to take shortcuts using the sample? So that's what this is all about. 6.3, 1 and 2, questions number 1 and 2, where it says which ones are unbiased, which ones are biased. Go off of this list right here, okay? Which ones are typically biased and which ones are typically not biased. And then number 3 and then the backside are going to be the same as what we had before. You can, in your good estimator, go off of what the results show here, okay? Not the results from 1 and 2. Okay, go off of what your results say for this data in particular. Okay. All right. So hopefully that was not terribly confusing. Just go through it just like we did this last example. Okay. All right. Good luck.